January 1944, Westward Ho, Devon. A pebble ridge overlooks a gray beach where the English Channel meets the shore in cold, methodical waves. Admiral stands with binoculars. Generals cluster behind him. Military photographers crouch at the ready. A cinematographer named Louis Klemantaski adjusts his telephoto lens, framing the landing craft that's just appeared offshore. Inside that craft sits something that looks like a giant cotton reel wrapped in rockets. The signal fires. 70 cordite rockets ignite simultaneously. The thing rolls forward out of the landing craft into shallow water. 10 feet of wooden wheel studded with steel treads, connected by a drum that, if this were not a test, would contain 2 tons of high explosives. The great Panjandrum has launched. For 50 meters, it works. The wheel spins, rockets scream, sand sprays, the brass nod approvingly. Klemantaski films steadily. An officer's dog, an Airedale Terrier named Admiral, after the explosive, watches with canine fascination. Then the first rocket clamp fails. The projectile detaches, spiraling over the heads of spectators. Then another, then 3 more. The Panjandrum lurches violently to starboard. It begins to weave. The admirals lower their binoculars. The general stops smiling. Klemantaski, viewing through his telephoto lens, misjudges the distance. The weapon is heading straight for him. He runs. The admirals dive behind the pebble ridge, landing in barbed wire entanglements installed for coastal defense. The generals scatter. Admiral the dog, displaying the intelligence that earned dogs their reputation as man's best friend, chases after a loose rocket like it's a thrown stick. The Panjandrum careens back toward the sea, trailing fire and cordite smoke. It hits the sand, disintegrates in violent explosions. Rockets tear across the beach at ballistic speeds. The brass haul themselves out of the barbed wire, bleeding from minor cuts, covered in sand. Dignity thoroughly shredded. The weapon designed to breach Hitler's Atlantic Wall had just turned on its creators. The project was scrapped immediately. The only casualty of the great Panjandrum's entire testing program was British pride. This is the story of World War II's most spectacular engineering failure and the weapon that nearly killed everyone except the enemy. If you want to hear more stories like this about the weird weapons of WW2, hit that subscribe button now. The Great Panjandrum looked like something a child might draw. 2 massive wooden wheels, each 10 feet in diameter, 1 foot wide, rimmed with steel treads, connected in the middle by a drum axle. Around the circumference of both wheels, 70 cordite rockets arranged in neat rows, ready to ignite. Inside the drum, 4,000 pounds of high explosives. The design payload would blow a hole through 10 feet of reinforced concrete. The design speed, 60 miles per hour. The design purpose to roll off amphibious landing craft, storm up the beaches of Normandy, and smash through Hitler's Atlantic Wall, creating a breach wide enough for British tanks to pour through. The actual result? Chaos, terror, and the most cinematically perfect failure in British military history. The name came from 18th century playwright Samuel Foote's famous nonsense verse. So she went into the garden to cut a cabbage leaf to make an apple pie, and at the same time, a great she-bear coming up the street pops its head into the shop. What? No soap? So he died, and she very imprudently married the barber, and there were present the Pickaninnies and the Jobblies and the Garulis and the Grand Panjandrum himself, with the little round button at top, and they all fell to playing the game of catch as catch can till the gunpowder ran out at the heels of their boots. The name was appropriate. What followed would be equally absurd. The Panjandrum emerged from the Directorate of Miscellaneous Weapons Development, the DMWD, a division of Britain's Admiralty that developed experimental weapons. Some of their inventions changed naval warfare: the Hedgehog anti-submarine mortar, the Squid depth charge system. Others did not. Cultivator number 6, an enormous trench-digging machine championed by Winston Churchill himself, proved equally useless. The Great Panjandrum would join it in the halls of inspired failure, but the idea, on paper at least, made sense, which is why dozens of engineers, thousands of pounds, and months of testing were devoted to making a giant wheel bomb work, despite every indication that it absolutely would not. By late 1942, the strategic situation was clear. Germany controlled most of Europe. The Soviet Union was bleeding the Wehrmacht white in the east. But for Britain, the path back to the continent meant crossing the English Channel and storming fortified beaches. Hitler knew this. The Atlantic Wall was his answer. Stretching from Norway to Spain, the wall consisted of tens of thousands of bunkers, pillboxes, and artillery positions. At key invasion points, particularly around the Pas de Calais, the closest point to England, the defenses were strongest. 10-foot walls of reinforced concrete, 7 feet thick, machine gun nests with interlocking fields of fire, hidden minefields, tank traps, artillery zeroed on the beach approaches, garrison troops dug in and waiting. British intelligence assessed the problem. Any conventional infantry landing would become a slaughter. Pre-invasion bombardment might suppress, but wouldn't destroy concrete fortifications. Aerial bombing lacked the precision. Even if troops reached the shore, they'd be pinned on the beach, unable to advance. Mowed down by artillery and machine guns from protected positions, the tanks that would break the deadlock couldn't land until the beach was secured. But the beach couldn't be secured without the tanks. Classic military dilemma. Winston Churchill had issued his directive to the newly formed Special Operations Executive: set Europe ablaze. Easier said than done when Europe was protected by the most extensive fortification system ever constructed. The DMWD received its assignment: find a way to breach the Atlantic Wall. The specification was simple to state and nearly impossible to achieve. What they needed was an unmanned device. Couldn't risk lives delivering it. Must be launched from a landing craft while still in the water. Amphibious then, must travel up a beach at sufficient speed to avoid enemy fire. Must carry enough explosive to breach 10 feet of reinforced concrete. Must navigate obstacles, barbed wire, tank traps, beach debris, craters from pre-invasion bombardment. Must detonate reliably on target impact. Must be manufacturable quickly and cheaply. Must work on the first attempt because there would be no second chance on D-Day. Oh, and it had to be ready within months because invasion planning was already underway. The specifications seem impossible. Enter Neville Shute Norway. Yes, that Neville Shute, the aeronautical engineer who would later become famous as a novelist. At the time, he was working for DMWD, applying his engineering mind to problems that conventional military thinking hadn't solved. His concept was brilliantly simple: a rolling bomb, 2 large wheels connected by an axle drum packed with explosives. Rockets attached to the wheel rims would provide propulsion, spinning the wheels, rolling the device forward. The faster it spun, the more stable it should become, like a gyroscope or a bicycle wheel. Slow it down and it wobbles. Speed it up and it tracks straight. The theory was sound. The mathematics checked. On paper, it would work perfectly. Reality had other plans. The great Panjandrum's design emerged from Schute's team through late 1942 and early 1943. Every component represented an engineering decision, a compromise, a calculated risk. The wheels, 10 feet in diameter, constructed of wood with steel treads. Why wood? Weight. All steel wheels would be too heavy to handle, too expensive to manufacture quickly. The wood had to be strong enough to support the weight, but light enough to accelerate quickly. 1 foot wide to distribute weight across sand without sinking too deeply. The drum axle, steel cylinder, designed to hold 4,000 pounds of high explosives when operational. For testing, sand would substitute for the payload. Same weight, different consequence when things went wrong. The drum measured approximately 5 feet long, 3 feet in diameter. Impact fuse would detonate on contact with concrete target. The propulsion system, 70 cordite rockets arranged around the circumference of both wheels. Why 70? Calculations showed that to achieve 60 miles per hour with 4,000 pounds of payload, approximately 35 rockets per wheel were needed. The rockets were slow-burning cordite units, naval rockets typically used for ship-to-shore bombardment. The mounting, each rocket attached to the wheel rim via steel clamps. The clamps had to be strong enough to withstand the acceleration forces, but light enough not to unbalance the wheel. They had to hold the rockets at precisely the correct angle, slightly angled inward and backward, to create both forward thrust and rotational spin. The theory predicted that once all 70 rockets ignited, the device would accelerate rapidly, reach operational speed within 50 meters, maintain that speed for several hundred meters, and crash into its target with devastating kinetic and explosive force. A tank-size hole would appear in the Atlantic Wall. British armor would pour through. D-Day would succeed with minimal casualties, but theory and reality parted ways at first ignition. The engineering challenges were more fundamental than anyone anticipated. Challenge 1: simultaneous ignition. Getting 70 rockets to light at exactly the same moment proved nearly impossible. Cordite rockets of that era used chemical fuses with inherent timing variation. One rocket might ignite 0.3 seconds before its neighbor. That fraction of a second meant unequal thrust. Unequal thrust meant wobble. Wobble at 60 miles per hour meant catastrophe. Challenge 2: sustained burning. The rockets needed to burn for precisely the same duration. In practice, manufacturing variances meant some rockets burned longer, others shorter. When rockets on one side burned out before the other, the remaining thrust pulled the device in a curve. The faster it traveled, the more violent the curve became. Challenge 3: clamp failure. The acceleration forces were immense. Steel clamps held initially, but weakened as vibration and thermal stress accumulated. When a clamp failed, the rocket detached. A 20-pound rocket flying free at random angles was dangerous. More importantly, losing rockets created thrust imbalance. The Panjandrum would lurch toward whichever side had lost propulsion. Challenge 4: beach conditions. Sand resistance varies with moisture content, compaction, and slope. Wet sand near the waterline offers different traction than dry sand higher up. Any differential in resistance between the two wheels caused the device to turn. The team installed steel treads to grip better, but this only partially solved the problem. Challenge 5: gyroscopic effects. A 10-foot wheel spinning at high speed creates powerful gyroscopic forces. These forces resist directional changes, which sounds good until you remember there's no steering mechanism. If the panjandrum started turning, gyroscopic forces would help it continue turning. It would describe a wide arc, potentially back toward friendly forces. Challenge 6. Unstoppable momentum. At operational speed with full payload, the great panjandrum would possess enormous kinetic energy. If it went off course, there was no emergency stop, no brakes, no remote detonation. It would go where physics took it, and physics cared nothing for military planning. The team tried solutions. They added a third wheel in the center for stability. It made things worse. Now 3 wheels had to remain synchronized instead of 2. They attached steel cables as improvised reins, thinking ground crews could steer from a distance. The cables snapped under the forces involved, whipping back across the beach like bullwhips. They added more rockets, reasoning that more thrust meant faster acceleration, less time for things to go wrong. This increased the violence when rockets failed. They tried thicker clamps. The clamps held longer but added weight, reducing overall performance. With every modification, the fundamental problem remained. The great panjandrum required perfect conditions to work. Perfect rocket ignition, perfect rocket burn duration, perfect beach surface, perfect trajectory from launch point to target. War offers none of these, but the engineers persevered. The mathematics said it should work. The concept was elegant. The need was genuine. Surely the next test would prove successful. It did not. The prototype was constructed in Leytonstone, East London, in August 1943. Security was paramount. The device was transported by night to the testing grounds at Westward Ho in Devon. The location was chosen because its beach resembled the suspected Normandy landing sites, wide, gently sloping, backed by modest bluffs. There was one problem with this choice. Westward Ho was also a popular seaside resort. Despite DMWD warnings about the danger of the weapon being tested, holidaymakers flocked to watch. The secret weapon was tested in full view of hundreds of civilians from the very first trial. Security was thoroughly compromised. If German intelligence had any competence at all, they knew about the panjandrum within days. September 7th, 1943, the first test. The team took precautions. Only 18 rockets were fitted, barely enough for proof of concept. The payload was sand, not explosives. The device was loaded onto a landing craft, positioned offshore. The signal was given. The rockets ignited. The great panjandrum catapulted forward, across the landing craft ramp, into the water, and up onto the beach. For perhaps 20 meters, it performed as designed, wheels spinning, rockets screaming, sending up plumes of sand and spray. The engineers began to smile. Then several rockets on the right wheel failed. The thrust imbalance was immediate. The panjandrum veered sharply to starboard, accelerating as it turned. It described a long arc across the beach before toppling onto its side, rockets still firing uselessly at the sky. Also captured on film for posterity, an officer's dog, the aforementioned Airedale Terrier named Admiral, chasing the device across the beach before losing interest and pursuing a detached rocket instead. The image would become iconic, a dog obliviously playing while a weapon designed to breach the Atlantic wall rolled drunkenly in the background. The engineers were disappointed but not discouraged. It was, after all, the first test. Modifications would solve the problems. Late September 1943, second test. Location moved to Instow Beach, near the Torridge Estuary. Number of rockets doubled to 36. Same sand payload, same launch method from landing craft. This time, the Panjandrum traveled twice as far before veering off course, still ended on its side, still shed rockets that flew over spectators' heads, still demonstrated conclusively that the design had fundamental issues. The engineers made notes and continued modifications. October 1943, third test. The team added a third wheel in the center, between the two main wheels, hoping it would provide stability. The device was positioned on a wooden ramp at the low tide line instead of launched from a craft. The intent was to eliminate water-related variables. When the signal came to fire the rockets, nothing happened. Technical fault in the firing circuit. As engineers scrambled to diagnose the problem, the tide came in. Water engulfed the Panjandrum. The third wheel, less robustly constructed than the main wheels, collapsed under the combined weight and wave action. It was a pathetic end to a test that never began. Late October 1943, fourth test. The third wheel was abandoned. The rocket count increased to 70, full operational load. Steel cables were attached to both wheels, the idea being that ground crew could use them as reins to keep the device on course. This test looked promising initially. The Panjandrum launched successfully, rolled up the beach, gathered speed. Then it skimmed across a series of small craters left by a previous test, became briefly airborne, and landed facing back toward the sea. Rockets still firing, it rolled back down the beach toward the water. Some rockets detached and flew over the heads of spectators. Others exploded underwater, sending up spectacular geysers. When crew members tried using the steering cables, the forces involved were far beyond human strength to control. The cables snapped, whipping back across the beach at lethal velocities. Fortunately, no one was struck, but the danger was obvious. Despite these consistent failures, the testing continued. The mathematical models still predicted success. The engineering team made notes, planned modifications, scheduled additional tests. The problem, they assured their superiors, was solvable. The concept remained sound, just a few more adjustments. By January 1944, the engineering team had been working on the Panjandrum for 5 months. They'd conducted numerous tests. They'd made countless modifications. They'd spent thousands of pounds, and they still hadn't achieved a single fully successful test run. But they remained convinced this time would be different. This time they'd perfected the rocket clamps. This time they'd improved the steering mechanism. This time the great Panjandrum would prove its worth. Senior officials needed to see the weapon demonstrate its capability. If successful, mass production could begin. Dozens, perhaps hundreds, of Panjandrums would roll up the Normandy beaches ahead of the invasion force. The Atlantic Wall would be breached. Allied casualties would be minimized. It was worth one more test. The demonstration was scheduled for a cold January afternoon. In attendance, government officials whose names have been lost to classification, military brass including multiple admirals and generals, and most importantly for history, cinematographer Louis Klemantaski, whose camera would capture what followed for posterity. Also present, an Airedale Terrier named Admiral, belonging to one of the officers. The dog had attended previous tests and, despite the explosions and chaos, seemed to find the whole affair entertaining. 2 new Panjandrum prototypes had been constructed. Both featured the latest modifications. Full 70 rocket configuration, improved clamps, better cable steering system. Engineers ran final checks. Officials took positions on a pebble ridge behind sand dunes, what was judged to be a safe observation distance. Klemantaski set up his camera with a telephoto lens. The lens would allow him to capture detailed footage while remaining safely distant, or so everyone thought. The first panjandrum was loaded onto the landing craft. The craft moved offshore to the designated launch point. Engineers gave the signal. Igniters fired. 70 rockets ignited, not quite simultaneously, but close enough. The panjandrum lurched forward down the landing craft ramp, through the shallow water, onto the beach, wheels spinning, rockets shrieking, sand spraying in great rooster tails. It was magnificent. For the first 50 meters, everything worked. The device rolled straight. Speed increased. The VIPs nodded to one another. This was it. The weapon was finally proving itself. The engineers exhaled with relief. Then physics reasserted itself. The first rocket to fail exploded, rather than simply detaching. The explosion damaged adjacent rockets. They exploded in sequence. A chain reaction rippled around the wheel rim. Explosions, smoke, flying debris. The panjandrum lurched violently to one side, but it didn't stop. It kept accelerating. Now, traveling at perhaps 30 miles per hour, the device began to weave drunkenly back and forth across the beach. Each weave was wider than the last. More rockets detached, flying off at random angles. Some exploded in midair. Others skipped across the sand like flat stones on water. One landed in the surf and detonated, sending up a 20-foot geyser. The panjandrum's trajectory, which had started toward the concrete target uprange, began curving. Then it turned sharply. Now it was heading back toward the observers. Klemantaski, viewing the scene through his telephoto lens, was focused on capturing the technical details of the weapon's failure. Telephoto lenses compress distance, making objects appear closer together in the frame, but also making it difficult to judge actual range. He saw the panjandrum weaving across his field of view. What he failed to immediately realize was that it wasn't moving across his field of view. It was moving toward him. Someone shouted. Klemantaski looked up from his viewfinder. The great panjandrum, trailing smoke and fire, rockets exploding and detaching, was bearing down on his position at considerable speed. He ran. Professional cinematographer's instinct made him grab his camera before fleeing, but only just. He sprinted away from the beach towards solid cover. Behind him, the panjandrum continued its arc, now heading toward the VIP observation point. The Admiral saw it coming. So did the generals. These were men accustomed to facing danger with aplomb, men who'd commanded warships under fire, led troops in combat, stared down death with British phlegm and stoicism. They panicked completely. Admirals dove behind the pebble ridge, landing face first in the sand. Generals leaped in any direction that looked away from the oncoming wheel. Several fell into barbed wire entanglements that had been installed as part of the coastal defenses. The wire caught uniforms, tore skin, tangled limbs. Dignified senior officers flailed like caught fish while a rocket-propelled wheel of destruction careened toward them. And then there was Admiral the dog. A rocket had detached and was spinning across the beach, still burning, trailing white smoke. To Admiral, this looked exactly like a thrown stick, an invitation to play. The dog bounded after it with typical terrier enthusiasm, completely oblivious to the danger. The rocket exploded perhaps 5 meters ahead of the charging dog. The blast was substantial. Admiral, shocked but unhurt, finally concluded that this game wasn't fun after all, and returned to his owner, who was at that moment extracting himself from barbed wire with considerable difficulty and even more profanity. The panjandrum, having terrorized everyone present, changed direction one final time. It headed back toward the sea. For a moment, it looked like it might roll harmlessly into the water. Instead, it hit a slight depression in the sand, tipped over, and crashed onto its side. The remaining rockets, pointing in all directions, continued to fire. The device spun in place, throwing up sand until the rockets finally burned out. Then, in a finale appropriate to the entire project, it disintegrated. The drum split open, rockets tore free and scattered across the beach at terrifying velocities. Multiple small explosions created a rolling thunder of destruction. Silence followed, broken only by surf, wind, and the groaning of officers extracting themselves from barbed wire. Klemantaski, professional to the end, had captured the entire disaster on film. The Great Panjandrum project was terminated immediately. No further tests were scheduled. The device would not be deployed on D-Day. The Atlantic Wall would have to be breached through conventional means. As for whether Winston Churchill was present at this demonstration, records are unclear. What is certain, senior officials directly reporting to Churchill attended. These were men whose deaths would have represented a catastrophic blow to British military leadership. The Great Panjandrum had come within meters of killing them. In that sense, it had indeed nearly killed Churchill's command structure, if not the Prime Minister himself. The weapon designed to breach Hitler's Atlantic Wall had instead breached the dignity of Britain's finest military minds, and they were not amused. If you're enjoying this deep dive into Britain's most spectacular engineering failure, hit that subscribe button and let us know in the comments where you're watching from. Now, let's examine what the Germans and Americans were doing while Britain was building giant exploding wheels. The British weren't the only ones facing the Atlantic Wall problem. Every Allied nation preparing for D-Day had to solve the same basic challenge. How do you breach massive concrete fortifications while under fire? The Germans, interestingly, faced the inverse problem. They needed mobile explosive delivery systems for defensive operations and counterattacks against Allied armor. Their solution was the Goliath tracked mine, where the Panjandrum was massive, chaotic, and uncontrollable. The Goliath was small, precise, and methodical. It measured just over a meter long, half a meter wide, and carried either 60 or 100 kilograms of high explosive depending on the model. Battery-powered early versions could travel about 1.5 kilometers. Later, gasoline-powered models extended range but added mechanical complexity. Most importantly, the Goliath was remote-controlled. An operator protected by cover guided the device to its target via a trailing wire. Maximum speed was just 10 kilometers per hour, walking pace, slow, vulnerable to small arms fire, and limited by wire length. But it reached its target predictably. That made all the difference. The Germans manufactured approximately 7,500 Goliaths during the war. They saw extensive use on the Eastern Front and in Normandy. Results were mixed. The device was expensive to produce. Each unit cost about the same as a military motorcycle. The wire guidance was vulnerable to being cut by shell fire or simply snagged on battlefield obstacles. Crews had to remain relatively close to the front line to maintain control. Allied troops learned to simply shoot the Goliath with rifles. Enough bullet holes would disable the batteries or rupture the fuel tank. But here's the crucial point. The Goliath worked. It successfully destroyed tanks, bunkers, and fortifications in documented combat operations. It had limitations, certainly, but those limitations stemmed from the technology of the era, not fundamental design flaws. Given better materials, longer range guidance, more speed, the concept would improve. And indeed, modern military forces use similar weapons, remote control ground robots with explosive payloads. The German approach, slow, controllable, expensive, but functional. Accept limitations, succeed within constraints. The British Panjandrum approach, fast, uncontrollable, chaotic, non-functional. Ignore limitations, fail spectacularly. Now consider the American approach. The Americans, working with British designers, developed a suite of specialized armored vehicles known collectively as Hobart's Funnies, named after British Major General Percy Hobart, who championed their development. The Sherman Crab, a standard Sherman tank fitted with a rotating flail on the front. Chains attached to a powered drum would beat the ground ahead of the tank, detonating mines safely. Slow, methodical, but it cleared paths through minefields without casualties. The Churchill AVRE, Armored Vehicle Royal Engineers, a Churchill tank armed with a 290mm petard spigot mortar. It could throw a 40-pound flying dustbin explosive charge 80 meters to demolish concrete obstacles. Reloading took time, but it worked reliably. The Sherman DD duplex drive, a standard Sherman tank made amphibious through a collapsible canvas screen that provided buoyancy, powered by propellers driven off the tank's engine. It could launch from landing craft offshore, swim to the beach, then fight as a normal tank. These weren't elegant solutions. They were practical, crude even, but they shared one critical characteristic. A trained crew operated each vehicle. When something went wrong, and things always go wrong in combat, skilled operators could adapt, compensate, solve problems in real time. The technical specifications tell the story. Panjandrum, theoretical speed 60 mph, actual controllable speed 0. Successful combat deployments 0. Total casualties inflicted on enemy 0. British officers endangered during testing multiple. Hobart's Funnies, operational speed 515 mph. Successful combat deployments extensive throughout Normandy campaign and beyond. Enemy casualties significant. Allied casualties prevented through mine clearing and obstacle breaching substantial. Why did one approach succeed while the other failed so completely? Philosophy. The Americans and their British engineering partners accepted that 1940s technology couldn't create reliable autonomous weapons. They built controlled weapons operated by trained crews. When technology failed, and it frequently did, human skill compensated. The Panjandrum concept assumed perfect conditions, perfect rocket ignition, perfect surface, perfect trajectory. It had no provision for human intervention, no feedback mechanism, no course correction. It represented a fundamentally flawed assumption that mechanical precision could replace human adaptability in the chaos of warfare. The lesson, obvious in retrospect, wasn't learned until after numerous tests, thousands of pounds spent, and multiple near-death experiences for Britain's senior military leadership. Spectacular isn't practical. Complex isn't effective if it doesn't work. Autonomous isn't sophisticated when the technology doesn't exist to make it reliable. War rewards reliability over audacity. The Sherman crab clearing mines 1 meter at a time saved more lives than the Panjandrum's theoretical beach storming run would ever have saved, even if it had worked, which it didn't. Even if the Panjandrum's technical problems had been solved, rocket reliability perfected, guidance systems added, beach performance optimized, fundamental limitations would have prevented its success. Consider the tactical reality. D-Day beaches would be under fire. Artillery, mortars, machine guns, rifles. The Panjandrum had no armor. A single artillery shell landing nearby would likely trigger sympathetic detonation of the explosive payload. 2 tons of high explosive detonating on the beach would create a massive crater, certainly right in the path of advancing Allied troops, creating an obstacle instead of removing one. Even if it reached the Atlantic wall intact, what then? The device had to hit concrete dead on to detonate. If it struck at an angle or hit soft ground just before the wall or encountered a tank trap, the impact fuse might fail, or worse, detonate prematurely, leaving the fortification intact. And what if it worked perfectly? 1 Panjandrum creates 1 breach. The Germans would immediately pour fire into that breach. Allied forces trying to funnel through would face a killing zone. Military doctrine requires multiple breach points to divide enemy forces and create tactical confusion. How many Panjandrums would be needed? Dozens, all launched simultaneously, all somehow reaching their targets despite random trajectories? The mathematics of warfare don't support it. The weapon that works 100% of the time, creating predictable results under varying conditions, will always trump the weapon that might work brilliantly under perfect conditions but usually fails catastrophically. Some historians have suggested the entire Panjandrum program was deliberate deception, part of Operation Fortitude, the massive Allied effort to mislead German intelligence about D-Day's location. The theory, highly publicized testing, which certainly occurred, hundreds of civilians watched, would reach German intelligence. Germans would conclude that British plans to breach the Atlantic Wall meant heavy fortifications were being targeted, therefore the Pas de Calais, not Normandy. The theory has problems. First, actual resources and genuine engineering effort went into the project. Records show real frustration, real technical problem solving, real hopes for success. Second, easier ways existed to leak false information to German intelligence. Why build a real weapon, test it repeatedly, risk lives, and spend valuable resources just for deception? Third, the deception value is questionable. Knowing the British were developing beach assault weapons tells the Germans very little they don't already know. Simpler explanation, it was exactly what it appeared to be, an ingenious concept, well-intentioned engineers, inadequate technology, determination leading to blind spots, confirmation bias preventing objective assessment, institutional momentum making it hard to abandon a project once started. The Great Panjandrum was, quite simply, a bad idea that persisted too long. The actual D-Day solution, on June 6, 1944, combined multiple elements: massive naval bombardment, softened defenses, specialized vehicles, Hobart's funnies, breached obstacles and cleared mines, infantry demolition teams destroyed, specific fortifications under fire, airborne troops disrupted rear areas, overwhelming force at the point of attack. It worked, at terrible costs, certainly. Thousands died on D-Day and in the following weeks, but the invasion succeeded. The Atlantic Wall was breached. Europe was liberated. The Great Panjandrum would have changed nothing. In the best case, one or two might have successfully reached their targets, creating breaches. More likely, most would have veered off course, endangered Allied troops, or detonated prematurely. Worst case, a panjandrum loaded with 2 tons of high explosives careening into staging areas, landing craft, or command posts. Ironically, the weapon designed to save British lives posed the greatest danger to British lives. Here's a perfect coda to the story. In 2009, for the 65th anniversary of D-Day, enthusiasts at the Appledore Book Festival decided to recreate the Great Panjandrum. They built a 6-foot replica scaled down from the original. Instead of explosives, they loaded it with fireworks. Instead of 60 mph, they hoped for 24 kilometers per hour over 500 meters. The result? It traveled 50 meters before breaking down. Even in 2009, with modern materials and engineering knowledge, with no one shooting at it, with perfect beach conditions, and observers keeping a safe distance, the concept still didn't work. Sometimes an idea is just bad. No amount of determination, engineering skill, or patriotic fervor can overcome fundamental flaws. The Great Panjandrum's legacy is a lesson in knowing when to abandon a failing project, a lesson that cost time, money, and very nearly several admirals. January 1944, Westward Ho, Devon. Admirals diving into barbed wire, generals running from their own weapon, a dog chasing loose rockets, a cinematographer fleeing for his life, and in the middle of it all, the Great Panjandrum, 10 feet of wooden wheel wrapped in 70 rockets, spinning chaotically across a British beach, threatening everyone except the enemy it was designed to destroy. The weapon meant to breach Hitler's Atlantic Wall couldn't breach common sense. The Directorate of Miscellaneous Weapons Development created genuinely revolutionary weapons. The Hedgehog anti-submarine mortar sank U-boats throughout the war. The Squid depth charge system improved on the Hedgehog's success. The Mulberry harbors, those artificial floating ports, made the Normandy invasion logistically possible. British engineering produced remarkable innovations under desperate circumstances, but the DMWD also gave us the Great Panjandrum and Cultivator number 6, the giant trench-digging machine that proved equally useless, and numerous other concepts that looked brilliant on paper but collapsed on contact with reality. Innovation requires 2 components, brilliant ideas and hard-headed realism. Engineers must dream big, but they must also recognize when reality refuses to cooperate. The Panjandrum team had the first component in abundance. The second component was notably absent. They saw the mathematical elegance of rocket-powered wheels. They didn't see the practical impossibility of controlling 70 simultaneously firing cordite rockets with 1940s technology. They believed the next modification would solve the problems. They continued testing despite repeated failures. They mistook determination for wisdom. Confirmation bias is a powerful force. Each test that failed wasn't evidence the concept was flawed. It was evidence that more modifications were needed. Each improvement that didn't work suggested a different improvement should be tried. The engineers had invested so much time, reputation, resources that abandoning the project felt like admitting defeat. Better to risk British admirals than British pride. But sometimes the most daring plan is simply the most foolish. Sometimes unconventional weapons are unconventional because they don't work. Sometimes the elegant theoretical solution fails the moment it contacts messy reality. The Great Panjandrum represents British innovation at both its best and its worst. Best, incredible creative thinking, willingness to try radical concepts, determination to solve supposedly unsolvable problems. Worst, continuing long past the point where reasonable people would have quit, risking lives for a weapon that endangered its own side more than the enemy. That's British engineering in World War II. Brilliant, brave, absolutely barking mad, and occasionally capable of producing weapons that nearly killed their own generals while failing completely to harm the enemy. The most spectacular failure of the entire war. The weapon that history remembers not for what it accomplished, but for what it nearly destroyed. The dignity of Britain's finest military minds, and, almost, the senior command structure of the Allied forces preparing to invade Normandy. 2 tons of explosives, 70 rockets, 10-foot wooden wheels, 0 successful tests, and 1 very confused dog named Amonal. That's the legacy of the Great Panjandrum. If the story of Britain's most spectacular engineering failure entertained you, subscribe for more weird weapons of WW2, and let us know in the comments, where are you watching from today? The full footage of these tests exists and is remarkably entertaining, possibly the only value the weapon ever provided.